Okay, good morning, all the students. We'll now go with the last topic of this hypothesis testing, though it is not last part of this module. The last part of this main concept, that is testing the hypothesis. Okay, in the last class, we have seen how to compare two algorithms by using the confidence intervals and the t-test. T critical value, and we have also understood that T critical value will approach Z score in case the underlying distribution is following a normal distribution, right? So in that class we have understood how to compare two learning algorithms on the same sample set. Means if a machine learning model is made to learn from the same sample set by using algorithm A and algorithm B. Right, in this case, which algorithm is performing the better? How to measure which algorithm is giving better performance? For that, we have seen a k-fold validation model in which we divide the entire data set into k partitions, and each time in each iteration, you take one of the folds as test set and remaining other folds, k minus 1 folds, as training set. Okay, say if you have 10 folds, data set is divided into 10 parts. In that case, one part will be taken for test, is taken as test set, and the other 9 parts will be taken as the training set. So this happens for 10 iterations, during which every partition will undergo training as well as testing. In that case, you will have an unbiased estimate of the error. So that across all these iterations, first iteration, second iteration, third iteration, up to 10 iterations, at each iteration you will have some error. You will have some error in the prediction, right? That error's mean is taken. Errors across all the iterations, that mean is taken, and its difference by using algorithm A and algorithm B, considered as delta bar, is calculated. Okay, now based on that delta bar, we should be able to calculate the confidence interval within which the difference between these two learning algorithms performance fall into. Okay, this has been elaborately discussed in your previous class. Now in today's class, we are going to discuss on paired t-tests and the practical considerations underlying that. Okay, now before we described, in the previous session we described one procedure for comparing two learning methods given a fixed set of data. That is what I have told you now, k-fold validation, or sometimes we call it as k-fold cross validation, right? Now by dividing the data set into 10 partitions, k partitions. Now in this section, we discuss the statistical justification for this procedure and for the confidence interval defined by these equations. Why we need statistical justification? See, simply you're given a data set, you divide it into some k folds or k partitions and start iterating over those k partitions, each time taking one test set and remaining as training sets. You do it repeatedly, but is there any support for the method you have approached? Is there any statistical justification that your approach is a good estimator of the performance of the learning algorithms? For that, in order to obtain that statistical justification, let us proceed now. Now, what are the two equations for the confidence interval we have considered? The first one is delta bar plus or minus Tn k minus 1 S delta bar. You remember all these terms I have explained in the last video. Delta bar is the mean of all the errors across the partitions, across k partitions you have done. You have partitioned the data set into that mean error plus or minus Tn k minus 1. What is this T? It is called as critical value at n% confidence interval and k minus 1 degrees of freedom. Okay, this is same as your previous formula, mu plus or minus zn sigma. You remember? Now that same formula we are applying in a different instance. Here we are performing k-fold cross validation. For that we get the mean of errors across all the iterations plus or minus, instead of z score we are considering it as t score here, because this t distribution, underlying distribution, though it is tending towards normal distribution, we are considering it as a t distribution with n% confidence interval and k minus 1 degrees of freedom. What is this degrees of freedom? Each time when you perform the k-fold cross validation, kth partition, one partition is taken for test set and remaining k minus 1 partitions are taken for training set. Now, whenever there is some accuracy, whenever there is some error encountered in that training set, that can be distributed across k minus 1 partitions. So you can distribute the error across these k minus 1 partitions. This is called as degrees of freedom. Now say you have reserved 2 partitions for test set and only 8 partitions for training set. In that case, your degrees of freedom is k minus 2 out of 10. 10 minus 2 means 8 partitions you are using for training the learning algorithm, right? In that case, the degrees of freedom will be k minus 2. But here you are considering only one partition as test set and remaining k minus 1 partitions as training set. The degrees of freedom is k minus 1. So the degrees of freedom indicate that over how many partitions you can distribute the error that is encountered, this delta bar, right? So that is called degrees of freedom, k minus 1 multiplied by, what is this? Standard deviation for the sample. Standard deviation, here it is represented as S suffix delta bar. What is the standard deviation for this particular distribution? And how we define the standard deviation? It is equivalent to square root applied over the variance in the errors. Understand carefully. Square root applied over the variance in the errors. What is the variance in the errors? How do you calculate a variance of a set of data points in a sample? You calculate the mean of the sample and each data point's deviation from the mean, square it, sum them up and divide by the total number of data points. You will get the variance. Now apply square root over that, you will get standard deviation. Same we are approaching here. We are finding out the standard deviation of delta bar. Okay, so it is the mean delta bar, the estimated delta, that is the estimated error across all the iterations, minus delta I minus delta bar. What is this delta I? In each iteration, what is the error encountered? Now that is from that, in each error, what is the error encountered? From that you subtract the mean error, square it, sum it up for how many values? You made k partitions, right? So I equal to 1 to k, sum up all the deviations in the errors from the mean error multiplied by, what is this term? To find out the average of the variance, 1 by k into k minus 1. Normally for average you take all the k partitions, but now you are also considering k minus 1 term because one data partition is used for test set. So you can't distribute the error over that partition. That is why it is k into k minus 1. Got it, students? Now you apply square root over that. You will get the standard deviation S delta bar. Standard deviation of the mean errors. You have the errors distributed in this format. Now you already know the mean, that is delta bar. Now you wanted to calculate the standard deviation of this delta bar, that is deviation in this direction and in this direction. Variation in the mean error in this direction and in this direction. That will give you the standard deviation, that is S delta bar. Am I very clear now? Some students who join in the middle or who didn't attend the previous classes and right now attending this class will not understand anything. It is like you are watching some Korean movie with some Chinese subtitles. So don't get confused. Watch the previous videos. That will have the continuity to this topic. Okay, but students who are following very sincerely lecture after the lecture will easily understand this. We are trying to find out the mean error across all the iterations of the k-fold validation. Yes, that is delta bar. Now, we also wanted to calculate the standard deviation of this mean error. For this, say, distribution, we are assuming that all the underlying distributions are tending towards a normal distribution. Now we know the delta bar, that is mean errors across all the iterations. Now we are trying to find out the standard deviation S delta bar. Instead of sigma, we are using S here, so that you will not get confused between this paired t-test and other tests. Okay, so S delta bar is the deviation from the mean value with respect to the error that is encountered across all the partitions, across iterations. Okay. Now to understand the justification for the confidence interval estimate given by equation is to consider the following estimation problem. Now, in order to justify the confidence interval estimate given by this particular equation, you know very clearly what is this equation, right? Delta bar plus or minus critical value T at confidence interval N and K minus 1 degrees of freedom multiplied by standard deviation of delta bar. I'm reading out this mathematical expression. I'm not simply saying delta bar plus or minus T and K minus 1. Listen carefully how I am reading this, so that each time when you are understanding this concept, you also read this mathematical notation in complete English text, so that you will memorize that easily. Okay, so it is the mean error plus or minus the critical value T at confidence interval N and K minus 1 degrees of freedom multiplied by the standard deviation of the estimated mean error. Now, how to consider this as an estimation problem? Let us see. We are given the observed values of a set of independent identically distributed random variables. Consider that we are given this set of values, identically distributed random variables. Identically distributed random variables means they are drawn from the same distribution and they are drawn independently. Okay, one draw doesn't influence the other draw. One picking up of the point doesn't influence picking up the other point. There are no recommendations, right? It is completely independent draw of the random variables y1, y2 and so on up to yk. Now we wish to estimate the mean mu of the probability distribution governing this yi. Now how can you estimate the mean? How can you calculate the mean? The estimator we will use is the sample mean y. Y bar is called as sample mean. Y cap is called as the estimated value of y. Do not get confused between cap and bar. Okay, y bar is called as the estimated mean, or simply we can call it as mean. In this context, we call it as estimated mean or estimator, simply the estimator. Now the estimator we will use in the sample mean y bar. How do you calculate mean? Very simple, right? Add up all the random variables given here, all the data points given here, divided by the total number of data points. That is given as 1 by k, sigma I equal to 1 to k, all the values, sum them up first, yi values, sum them up and divide by total number of values, that is k. That will give you the mean. Adding up and taking the average, that's all. That is expressed in mathematical terms. Now, this problem of estimating the distribution mean mu based on the sample y bar is general. We know that already. For example, it covers the problem discussed earlier of using sample error to estimate true error. Do you remember in our previous sessions, when we have the sample error estimate, using that we are trying to find out the true error into which confidence interval it may fall. Right? We have calculated that. Now, the t-test applies to a special case of this problem, this kind of problem, the case in which individual yi follow a normal distribution. Now, listen carefully. When individual data points are following normal distribution, means most of the values are falling within a particular range, and very extremely less values and more values are falling on the tail side. In that case, when each individual yi is following a normal distribution, then automatically the entire set of values will follow a normal distribution, right? When each of the students are following the rules, then we say that the whole class is following the rules, right? In the same way, when each of the data points in the set of random variables is following a normal distribution, the entire sample also will follow a normal distribution. That is the bell curve, right? Now consider the idealization of the method for comparing learning algorithms given in table in the previous lecture. You remember in the previous lecture, the method for comparing learning algorithms: divide the data set into k partitions, take one partition for test set and k minus 1 partitions for training. We have that procedure, right? That consider that learning method, method for comparing the learning methods, okay? That k-fold cross validation. Now, assume that instead of having a fixed sample of data D naught, we can request new training examples drawn according to the underlying instance distribution. Now, let us think that we are not using the same sample D naught. We are just requesting for another new sample, new set of training examples drawn according to the underlying instance distribution. But the condition is they should be drawn from the same distribution, but a different sample. Let us consider. Now, in particular, in this idealized method, we modify the procedure such that on each iteration, though the loop it generates, through the loop, it generates a new random training set Si and new random test set Ti by drawing from this underlying instance distribution instead of drawing from the fixed sample D naught. So what we did is we already have D naught on which we performed cross validation. Now let us draw a different sample from which again we select the training set and test set. Now, in particular, the delta I measured by the procedure now correspond to the independent identically distributed random variables yi. Now, what is this delta I? In this case, when we have taken a new sample, now in this case, the delta I measured by the procedure now correspond to the independent identically distributed random variables yi. We have taken a different sample which are drawn from the same distribution but independently drawn. In that case, delta I pertains to that error associated with that particular new sample. Now, the mean mu of their distribution corresponds to the expected difference in error between the two learning methods. Now, if we check the two learning methods on this new sample, then the mean mu of their distribution means the average of their distribution corresponds to the expected difference in error between the two learning algorithms. Say we have taken learning algorithm A and learning algorithm B. Now the difference in these errors, okay, for that mean of the distribution is calculated. The mean of difference in the learning algorithms, errors obtained through the learning algorithms, that mu is taken. Now the sample mean y bar is the quantity delta bar computed by this idealized version of the method. Okay, now you repeat this process. In the new sample, you take 80% as training set and 20% as test set. You get some delta error, okay, between the two learning algorithms A and B. Now again, mix it up. Randomly you take another training set, another test set. Now when you apply the two learning algorithms, you get the difference between their errors. That is your next delta 2. That is error between them is delta 2. Next in the next trial, you will get delta 3. The difference in the learning algorithms in the third iteration. Remember here, I'm not making K partitions. I'm just doing my experiments randomly. In that case, I'm getting each time one delta value. Now add up all those delta values, errors in the learning algorithm, difference in the learning algorithms, add up all those values, you will get delta bar. Okay. Now the sample mean y bar is the quantity delta. What you're doing is the errors mean you're finding out. So what is your parameter of interest here? Errors. Then when you are finding out the mean of the errors, it is nothing but y bar, right? The parameter of interest is error, which is denoted by the random variable, random parameter that is going to be measured. Now you are trying to measure the random parameter y, which is error in this case. Now when you are finding the mean of the errors, it is nothing but mean of y. Okay, so the sample mean y bar is the quantity delta computed by this idealized version of the method. Now we wish to answer the question. What is that question? How good an estimate of mu is provided by delta bar? Means whether the normal distributions mu is same as the mean errors found across different experiments on the new sample. Between the two learning algorithms, what is delta? Delta is the difference in the errors of learning algorithm A and learning algorithm B for each experiment conducted on the main sample. Okay, now that delta bar, is it following a normal distribution mu? Did you see? Our problem now took a proper shape. I'm explaining again. You have taken a new sample. Now you are partitioning it each time into training set and test set, and you get some error with respect to learning algorithm A and with respect to learning algorithm B. Now what is the difference in the errors for the first experiment? Delta 1. What is the difference in the errors for second experiment between the two algorithms? Delta 2. And so on. You perform that experiment many times. That will give you delta 1, delta 2, delta 3 and so on. All the error estimates. All the errors across the experiments. Now add up all the errors, find the average, that will give you the mean error delta bar. Now what is the question is whether this delta bar is following a normal distribution. Whether the distribution of errors is following a normal distribution. How do you find out that one? Whether the distribution of errors between the two learning algorithms is following a normal distribution or not. How do you measure that? By calculating the errors mean, that is delta bar, and seeing whether it is equal to the mean of the normal distribution mu. If they are equal, then we can say that errors are following a normal distribution. We brought that question into understandable manner now. Now first note that the size of the test sets Ti has been chosen to contain at least 30 examples. So the sample to be sufficiently large, to make the test set to be sufficiently large, we should ensure that, we already assumed this, right? We should see that the test set should contain minimum 30 examples, 30 training examples, 30 data points. Okay. Now because of this, the individual delta I that is the difference in the errors of the learning algorithms, delta I. Okay, because of this, the individual delta I will each follow an approximately normal distribution due to central limit theorem. So whenever you have sufficiently large sample, then the errors may follow the central limit theorem, indicating that most of these errors fall within this range, within the moderate range, around the mean of the normal distribution. When we take like this a normal distribution, you know that this point is mu, and the deviation found is the standard deviation around this mu, right? Or we indicate it by sigma, sometimes S, sometimes sigma, okay, based on the context. Now, because of this, because of having sufficiently large sample containing 30 data points in the test set, the individual delta I, that is error associated with each experiment I, between the learning algorithms A and B, will each follow an approximately normal distribution. They follow normal distribution according to central limit theorem because the test set contains sufficiently large data points, that is greater than or equal to 30. Okay, hence we have a special case in which the yi are governed by an approximately normal distribution. Okay, this is the special case that this range of values yi are following approximately normal distribution. Now it can be shown in general that when the individual yi each follow a normal distribution, then the sample mean also follows a normal distribution. Common sense, right? If each of the values in y follows normal distribution, then whole sample also follows the normal distribution. Whole parameter also follows the normal distribution, right? The mean of the parameter also follows the normal distribution. Now, given that y bar is normally distributed, we might consider using the earlier expressions for confidence interval. Now, we understood that this y bar, that is the error in the difference in the errors of learning algorithms, that mean error is following a normal distribution, then why not we write the confidence interval expression like this directly, instead of using mu plus or minus t n k minus 1 s delta bar. Instead of writing it as plus or minus mu plus or minus critical value t at n% confidence interval and k minus 1 degrees of freedom multiplied by s standard deviation of delta bar. Instead of writing all this, because this delta bar is following a normal distribution, why don't we write directly like this, y plus or minus z and sigma, to make our representation more familiar like before, more easier to understand, which applies to estimators governed by the normal distribution. We'll do that. Unfortunately, that equation requires that we know the standard deviation of this distribution, which we do not. We can write it because it is following normal distribution. We can write it as y plus or minus z and sigma. In this, y is known, y bar is known, z is known, but standard deviation is not known because confidence interval is not yet calculated. Now, the t-test applies to precisely these situations. In this case, this t-test will be useful when the mean is known, when the estimated value of the distribution is known, but the standard deviation is not known. In that case, you go for paired t-tests. Important question they'll ask you in interviews. If they say, if mean of the sample is given, standard deviation is not given, which test do you prefer? Immediately you should be able to say it is a paired t-test, right? In the previous case, we have same sample being tested with both learning algorithms. Okay, we can easily do that because we know the mean as well as standard deviation. But when you don't know the standard deviation, when the standard deviation of a distribution is not given, then you can go for paired t-tests. So the t-test applies to precisely this kind of situations in which the task is to estimate the sample mean of a collection of independent, identically and normally distributed random variables. Okay, so in this case, we can use the confidence interval given by equations 1 and 2. In slide 4, we have that, right? These equations 1 and 2 we can take. In this case, we can use the confidence interval given by those equations 1 and 2, which can be restated using our current notation as, now we are changing into our current notation as mu equal to y bar, the mean of errors here represented by y. Because delta is following the distribution as y, we are simply writing it as y bar plus or minus critical value t calculated at n% confidence interval and k minus 1 degrees of freedom multiplied by s y bar, the standard deviation of this mean y bar that can be taken to calculate mu. That can be taken to replace mu, where s y bar is the estimated standard deviation of the sample mean, the new sample we have taken. So how you can represent this standard deviation of y bar? You know that, right? Instead of delta, we are just using y bar. It is the entire sample's mean and each data point's deviation from the sample mean, square it, sum it up and find out the average. And apply square root over that, you will get the standard deviation. Without square root, it is variance. With square root, this entire term, this entire representation gives you the standard deviation of y bar. And this also I have explained why we have taken 1 by k into k minus 1, because you are reserving one partition always for testing and you can't distribute the error on that. So you are distributing the error on k minus 1 partitions. Here, t n k minus 1 is a constant which is analogous to our earlier Zn. T critical value is same as your Z score value. I explained you how to locate this T distribution value also. You can just Google for T distribution tables, and in that for every confidence interval, 90%, 95% and 100%, for each degrees of freedom, 1, 2, 3, 4, what is the T value is given in the table. So you can locate for 95% confidence interval at 4 degrees of freedom, what is your T value? You can locate it easily. Okay, so in fact, the constant T and K minus 1, that is why it is a constant. It is given in a table already established. Now, in fact, the constant T and K minus 1 characterizes the area under a probability distribution known as the T distribution. Now, we call this distribution as T distribution because we are considering the critical value T. Just as the constant Zn, it is almost same as constant Zn, characterizes the area under the normal distribution. They both tend to follow. How you have equated T to Z? Because you understood that T distribution is following a normal distribution, we tend to equate this T distribution to T value to Z value, T score to Z score. Okay, now the T distribution is a bell-shaped distribution similar to the normal distribution, right? It is similar to the normal distribution. That is why we equated it to Z score, but wider and shorter. Wider and shorter means, say in normal cases, the normal distribution is like this, but in this case, it will be in this way. Wider, this interval is more wider and shorter, okay? But wider and shorter to reflect the greater variance. Did you notice here? Variance is higher. Then see, when you take the variance or standard deviation in this case, and in this case, the variance under the curve is higher. Okay, so to explain that, this T distribution is being taken. So the T distribution is a bell-shaped distribution similar to the normal distribution, but wider and shorter to reflect the greater variance introduced by using SY bar, that is the standard deviation of the mean of the parameter being measured, that is the error difference in the error between the two learning algorithms, what we are measuring, that is y. Okay, by using s y bar to approximate the standard deviation sigma y bar. We are trying to find out this sigma y bar. Now the t distribution approaches the normal distribution, and therefore t n k minus 1 approaches zn. T value will almost be equal to z score value. As the sample size increases, as k approaches infinity, means the sample size, minimum it should be 30, and as it grows, the t value will almost be similar to z score value. Now, the previous discussion justifies the use of confidence interval estimate given by the equation. Here, the confidence interval estimate, how it is calculated, it is given by this equation, delta bar plus or minus critical value t at confidence interval n and k minus 1 degrees of freedom multiplied by the standard deviation of the mean error. Okay, that will help you to calculate the confidence interval. That will help you to calculate the interval within which the range of values fall into. So in this case, where here we wish to use the sample mean y bar to estimate the mean of a sample containing k independent, identically and normally distributed random variables. So we wish to use the sample y bar to estimate the mean of sample containing k independent random variables. Now, this fits the idealized method in which we assume unlimited access to examples of the target function. Now, if the data points are too many, means the size of the data set is too high, that is an ideal condition. In normal cases, you may not be able to collect large data sets. The data points in a data set may be limited. Okay, so this particular interpretation what we are using for calculating, for justifying the use of confidence interval, this fits the idealized method in which we assume unlimited access to examples of the target function. You have large number of data points, then this would be sufficient. But in practice, given a limited set of D naught, this justification does not strictly apply. We can't say that T distribution may follow a normal distribution and its T value almost equal to Z value. We can't say that. Why? Because the data, when it is limited, there is always a doubt whether it would follow normal distribution or not. So in practice, the problem is that the only way to generate new delta I is to resample D naught, dividing it into training and test set in different ways. Okay, so when the training set is limited, in that case, in order to calculate the difference in the errors between the two learning algorithms, that is delta I, you don't have any other option but to resample this D naught. Each time take a different sample from the data set. Okay, in order to divide them into training set and test set and find out the errors in the learning algorithms. Okay, so the delta I are not independent of one another in this case because they are based on overlapping sets of training examples drawn from the limited subset D naught of data rather than the full distribution D. So from the entire data set, we are not taking the training set and test set. First, we are taking a sample from the entire data set, and that sample we are dividing it into training set and test set. That is why delta I is not independent of one another. Training set and test set may be overlapping in this case because we have very limited amount of data points in the data set. We have just drawn a sample. We are not using the entire data set. In that case, delta I may not be independent of one another. In this case, they may have influence on each other. The error of one iteration may influence the error in the other iteration. Now, when only a limited sample of data D naught is available, several methods can be used to resample D naught. What is one method? K-fold method. This we know already. Dividing the data set into K partitions, taking test set and K minus 1 partitions for training set. Okay, that is one method in which D naught is partitioned into k disjoint equal sized subsets. Now, in the k-fold approach, each example from D naught is used exactly once in test set and k minus 1 times in a training set. That is quite obvious. Now, a second popular approach is to randomly choose a test set, another approach, completely different from cross-validation. What is that approach? The second approach is to randomly choose a test set of at least 30 examples. Okay, test set we are taking with 30 data points from D naught, that is the sample we have taken from the main distribution D. Use the remaining examples for training. Say there are 100 data points in this D naught. 30 randomly you have chosen for test set and remaining 70 data points you use for training set. Then repeat this process as many times as desired. Not only 10 times, not only 20 times. You may repeat it for how many number of times you want based on the time available for training. What is the difference here? In k-fold cross-validation, you're dividing it into k partitions, each partitions having at least 30 data points. There is limitation in the times of in the number of times you perform that experiment. That is k times, because you divide the data set into k partitions. But in this case, there is no limitation in the number of times you perform the experiment. You can do it as many times as required, but randomly selecting test set and training set with minimum 30 data points in the test set. Minimum. It can be more than that, but minimum 30 points in the data set. Now, this randomized method has the advantage that it can be repeated an infinite number of times. It is based on your patient's interest and time. To shrink the confidence interval to the desired width. What will happen in this case? In this randomized method, as you go on testing as many number of times as you want, when you take the confidence interval may actually shrink. The confidence interval, if you take like this, it may actually, it used to be in this way, right? 95% confidence interval. But because you're repeating this experiment many times, each time taking randomly selected test set and training set, the confidence interval may shrink because you're becoming stricter and stricter in your validation process. So the confidence interval may shrink to 80%, 70%, and even to 60% also, within which range the difference of errors of the learning algorithms fall into, right? In contrast, the k-fold method is limited. But when we compare the k-fold method, it is limited. You perform it only k number of times by the total number of examples, by the use of each example only once in a test set, and by our desire to use samples of size at least 30. In k-fold cross-validation, we have a limitation that every partition should contain at least 30 data points, and each data point will undergo training once and training k minus one number of times and testing only once, like that. Okay, so this is completely different from the randomized method where you repeat the experiment for indefinite number of times. There is no limitation. Okay. So to summarize, no single procedure for comparing learning methods based on limited data satisfies all constraints we would like. You have to remember, as a machine learning expert, you can't simply state that this algorithm is good for this data set or this algorithm is good for this data set. Based on the approach you select for cross-validation and based on the approach you select to prefer between the learning algorithms, and based on the evaluation metrics, you will have to decide which learning algorithm best suits your context, which best suits your data. Okay, so this is not a 1 day or 2 day process. When you're asked to develop a machine learning model, you have to work on it iteratively for more number of days in order to find out the best performing algorithm, making some assumptions. Again, you can't simply say more strict. You should have some assumptions. Means you should say take some points as granted. Okay, this is following a normal distribution. This will consider only conjunction of the attributes, no disjunction of the attributes, and this should contain only the simplest decision tree. Like that, you have to make some assumptions in order to select the best machine learning model on the with respect to the data at hand. Now, it is wise to keep in mind that statistical models rarely fit perfectly the practical constraints in testing learning algorithms when available data is limited. When the data is limited, they may not show compliance with the statistical models. But if the data is large enough, in that case, normally they satisfy the statistical models. So when the data is limited, you can't expect each time that they should be in accordance with the statistical models. Nevertheless, they do provide approximate confidence intervals that can be of great help in interpreting experimental comparisons of learning algorithms. So what would be the approximate confidence interval within which the difference in the errors of the learning algorithms fall into? Those will be the main criteria for us in order to select between the learning algorithms. But in order to calculate that confidence interval, you should know the distributions, mean, standard deviation, t-score, z-score, all these play very important role. That is why you have to understand all these terms in order to calculate the confidence intervals within which the difference in the errors of learning algorithms fall into in order to compare the learning algorithms, which one is performing the better. Okay, in the next coming session, this hypothesis testing part is completed. In the next coming session, we are going to see what is instance-based learning. So far, we have seen only supervised learning kind of algorithms, right? Where you have training labels, labels for training set and the test set already given. But when such kind of labels are not given, in what way the learning will be made? Okay, that will be discussed under instance-based learning, and with an emphasis on k nearest neighbor learning. Any doubts, students, in today's class? Students, you have any doubt? Just go through all the videos of hypothesis testing. This may seem to be irrelevant for you, why we are actually learning this kind of statistical terms and all, but when you pursue a career in this data science, then you will understand, then you will recollect what all terms we have learned during your course. Okay, so that will ring the bell. Yeah, once I have learned about this hypothesis testing, once I have learned about this level of significance, once I have learned about this confidence interval, that time you will be able to recollect all these terms what we have discussed in this chapter. Okay, so that time you will easily understand the context in which you are trying to implement that knowledge, right? So we'll meet in the next class with instance-based learning.